Hello and welcome to HES and Rolls presentation today. Today we're going to be presenting on charging big cells, inverter settings, equalizing and maintenance. We're with Rolls battery guru Steve Higgins. He is going to be taking care of the presentation, and we'll be doing a Q&A following the presentation. If you've got questions, please type them in, and I will be posing them for you at the end of the presentation. So without further ado, Steve, over to you.
Hello, everybody. My name is Steve Higgins. I'm the Technical Services Manager for Rolls Battery Company. You see my address, my phone number. Feel free to give me a call if you have any questions. I'll be happy to answer them afterwards. We're going to talk a little about Rolls batteries. I'm going to get right into it. Again, please make sure if you have any questions, the type them in. We'll be happy to answer them at the end. First thing about Rolls. Rolls battery was established in 1939 as Surrette battery. In 1959, it moved to Spring Hill, Nova Scotia in Canada as Rolls battery. We manufacture flooded cell or deep cycle AGMs, lead acid AGM batteries. Right? AGMs are flooded lead acid batteries. At this time, we don't manufacture lithiums or some of the newer battery technologies coming out because, frankly, they're just not manufacturable for reasonable cost and price. We are ISO 9001 certified as back in 2002. Renewable energy represents about 40% of our production on a normal basis. We have inventory in 10 different countries, 4 continents, and there's probably 40,000 different off-grid systems all over the world installed. Africa, Asia, Latin America, all those wonderful places. Just a general product line. Our flooded acid batteries, we range from 80 amp hours all the way up to 3,300 amp hours. We make a fairly large line, or I'm sorry, 2,400 amp hour capacity, all in 2, 4, 6, 8, 12 volt cells, different cells. So this, you see the line here, actually this needs to be updated because we still have the S460s and the S530s listed on our batteries. For the AGM line, we manufacture from 85 amp hour all the way up to 3,300 amp hour. The most common of those would be the S6 460 AGM or the S12, S2 1275 AGM. If you are looking at the larger capacity AGM batteries, there's a little bit different way you have to hook them up, so that, and the lead times are quite a bit longer, usually around 10 to 16 weeks, depending on how many you're ordering. Just a little on the series 4, so we divide our batteries up in several different series of batteries. The first series is the series 4000 flooded lead acid. These are competitively priced, easily movable L16 type chassis. You know, the series 4000 is the most common ones of the L16 type chassis, the S460, the S480, the S530, S550, S620. Those are the most common ones that we probably sell, and our distributors sell quite a bit of them. They have a relatively large liquid reserve. We use a little bit larger plate, which gives us longer cycle lives and larger capacities. Now, typically your average customer on a Series 4000 battery, you're looking at your average customer gets between 8 and 10 years worth of operational life. Your perfect customers who are taking care of them and they're not beating the living daylights out of them. You know, I've got a guy I talked to just a couple days ago that had a set of L16s for 15, 16 years before we replaced them, and they're in their second home now. So 50% depth of discharge cycling, you're looking at 1,280 cycles. There's a 7-year warranty, the first 2 years of which are a replacement warranty. Then the next 5 years are a prorate warranty. Most common of these are the S480, the S550, and eventually there'll be a S605 to replace the S600 that was discontinued back January last year. All of our batteries, most of our batteries are what's called lead antimony. We do make a calcium battery called the FC420. Calcium batteries are designed more of a float service. So calcium batteries are perfect for your grid tie application where you're just going to be selling off excess power to the grid, or it's a grid backup application where you don't have a lot of grid service interruptions. That calcium battery will sit there and it's happy to sit there in a float surface. If you do the same thing with a lead antimony battery, it uses quite a bit of water, and it also can develop some, for the lack of a better term, something of a memory if you don't exercise it. I'm sure everybody's heard that the best thing you want to do is you want to exercise your lead acid batteries, to a point that's true. Typically, if you do have a lead acid battery on a float surface, you want to give it about a 10-15% cycle about once a quarter to keep it active. The next line of our Series 4000s, pretty common ones, are the 2-volt L16s, the S1450s, the S1660s, and the S1860s. Those replace some of the older batteries that we had. Again, unfortunately, I don't have the updated pictures yet, so the pictures here aren't exactly what you're going to see. These batteries are 2-volt cells, so if you have a 12-volt or sorry, a 24-volt system or a 48-volt system, instead of doing multiple parallel strings, where you're doing 3, 4, 5, 6 parallel strings of batteries, you can accomplish the proper battery bank size with 1 or 2 strings of batteries. Much more efficient than stringing a bunch of 6-volt batteries together. The Series 5000 batteries are the next most common series batteries that we manufacture. The amp hour capacities range from 300 amp hours all the way up to 2300 amp hours. Their warranty is 7 years. It's a three-year replacement with a 7-year prorate. They have a dual container. Typically, you're going to see roughly about 3,200 cycles at 50% depth of discharge versus the 1,300 cycles. Oops, something's going on there. There's the double wall container. Basically, it's an advantage over steel trays because you're not dropping things into it. Again, the plates are higher or heavy capacity. The large liquid reserve, so you get excellent electrolyte flow within the battery while charging. Everything's pretty solid with these batteries. So the next series of batteries that we manufacture are the AGM series batteries. They're a maintenance-free sealed battery, available 6, 12-volt, and 2-volt options. The biggest thing about these is they are the maintenance, what's basically a maintenance-free battery. The one comment I have on maintenance-free batteries is there's no such battery that doesn't require maintenance. You still have to check connections on any AGM that you sell or install into the system, because we'll see a little bit later what happens to you when you leave connections loose on a battery. These are excellent batteries for applications where customers aren't going to cycle them pretty heavily. You're looking at about 1,250 cycles on these batteries for a lifetime. For your city connected backup system, for maybe even a grid tie system, these batteries would work fine for customers who are expecting multiple, or not daily outages, but monthly or weekly outages. One of the things when you're selling batteries to definitely keep aware is understand how batteries work. One of the issues, one of the things that people that I deal with every day is when I talk to people on the phone, one of the first things they hear when I say sulfation, they think that I'm in the process of telling their battery's not covered in warranty. Well, here's the definition of sulfation and what it is. Sulfation is natural. Sulfation is something that happens to a battery as soon as you take a battery off of a charger, it starts to sulfate. So sulfation is a perfectly normal situation that goes on with a battery, and it's just a chemical reaction that happens in the battery. What happens with that chemical reaction is, here are the chemical equations of what's going on with the battery. So you have basically 2 different plates in the battery, and there's 2 different reactions that are going on inside that battery. Now I'm going to put down here the definitions of what the chemical terms are here. Sorry about that. I've got this thing on my screen that's bothering me. So at the positive plate, what you have is you have the PbO2, which is lead oxide, 3H is hydrogen, H2SO4, which is sulfuric acid, and 2E is electrons. So basically what that is those 3, when you're generating those 4 things at the positive plate, you're creating lead sulfate plus water. Because what's happening is the H2SO4, the SO4 is leaving the water, and populating itself on the lead, making PbSO4. So basically what you have is PbSO4 plus 2 H2Os, which gives you water, okay? At the negative plate, what you have is you have lead, and basically it's a lead plate with a sulfuric acid mix. As you discharge that battery, it becomes PbSO4, so the lead changes from lead to lead sulfate. And then of course you get a release of hydrogen and electrons. You know, the electrons in current, and hydrogen comes out of the battery as a gaseous form. Another thing that comes out of the battery is oxygen. So what you want to do is, oxygen is not as flammable as hydrogen. You want to try to prevent hydrogen buildup in the whatever battery enclosure you've got of less than 2 to 4%. Anything greater than 4% is extremely explosive, and this is where you get problems with ignition of it, and that tends to blow the tops off the batteries. And that's why most battery manufacturers will tell you when you blow the top off a battery, it's not under warranty, because it was actually a hydrogen ignition which caused it. These formulas work in reverse when you're charging the batteries. What you're doing is you're putting in the electrons to the plates, and you're converting the PbSO4 back into PbO2 or lead oxide, and then the lead plate, the lead sulfate plate's changing back into a lead plate on the negative battery. So basically, what's happening there is the sulfation is accumulating on the plate and being pushed off the plate. What you want to try to avoid is leaving the lead sulfate on the plate for any extended period of time, because it will harden and crystallize. And once it's done that, then you have to raise the temperature or boil the sulfation off with an equalization charge. We'll get into equalization a little bit later, but we'll get more into that a little bit later. So one of the things that whenever you call a battery manufacturer, they're going to ask you is to determine what the state of charge is you can look at the specific gravity of the acid, and that'll give you a basic idea of how much actual SO4 sulfate is in the water or the electrolyte versus the sulfate being on the plates. One of the things you want to be careful of is specific gravity is going to lag on recharging. So what you want to do is, when you charge your batteries, you want to give them a couple, 2 or 3 hours for them for that mixture to mix to get a proper specific gravity measure. Now, if you do have a temperature compensated hydrometer or temperature compensated refractometer, or if you're making the temperature compensation calculations, you can measure it on the fly, as long as you understand that they're going to be a little higher, a little lower. Now, based on the temperature compensation scales, actually here's the specific gravity. So between 1255 and 1280 is what would be considered a good 100% charged. For a solar system, off-grid, grid-connected, for a solar system where the batteries aren't seeing a constant 4 to 6 hour charge every single day, typically you want that specific gravity between 1265 and 1275 is going to be the sweet spot. Most customers with voltage-controlled chargers out there nowadays, even the Schneider, the Outback, Magnum, they're all voltage-controlled chargers. You're going to have to do a lot of charging to get the batteries up to 1280 in most cases, or the customer is going to be underutilizing their battery bank. Now, when it comes to temperature compensation, I don't know if everybody can see this chart, but the temperature compensation factor, you got to be careful, is it acts in reverse to most people, what most people think. The warmer the electrolyte, the higher the specific gravity due to that lagging, the mixture lagging. So if you have a electrolyte temperature at 32 degrees Celsius, you're going to add 0.006 to that measurement. If your electrolyte is down to 10 degrees Celsius, then you're going to subtract 0.006. Something to keep in mind, especially for where North America, Canada, basically in general, what you want to be careful of is that a full battery at 1265 to 1280 specific gravity will not freeze until negative 94 degrees Fahrenheit. A battery that is at a 50% state of charge, or a 1220 specific gravity measurement, will freeze at 20 degrees Fahrenheit. So it's very important for the customers who have the remote cabins to make sure that you get those batteries, you keep those batteries as charged as possible, so that they don't freeze. Freezing's not a good thing. You'll see some pictures of freezing damage a little bit later. Moving on, battery bank sizing, some of the things to consider when you're doing battery bank sizing. Oops, sorry about that. Is there's really three different types of systems. You have the grid tie, no batteries, solar only. Basically, when the utility fails, the customer has no power. What's pretty common with this customer is they're going to call you up and tell you they have a 3-bedroom house. How much solar do they need? Of course, nobody knows until you do. The only way to really tell how much solar, or how much battery, or how much anybody needs, everybody in this room probably understands that you've got to know how much electricity they actually consume. If you make any guesses, that will eventually come back and bite you. The next customer is a grid backup, typically a small backup, power essential loads, lights, TV, what I call lights, TV, and cold beer. You want to power the refrigeration, you want to power the lights, you want to power the information in case there's an emergency or something going on, or they lose power because of a storm or something like that. A lot of times, if it's a grid backup system, a lot of these systems will be sized for a 80% depth of discharge because they're only seeing 1 or 2, 3 disconnections a year. At that point in time, they're not really worried about how many cycles they're putting on the battery. The next customer are the fun customers. These are the customers that live out in the middle of nowhere. They're the ones that call you up just because they want to talk. They're the ones that they're different because they want to live. They're different because they're different. They don't mind living 600, 700 miles away from any major city. These customers, you have to know 100% for certain what their load profile is. One of the things you want to do is you want to go through and do a real gut check load profile. I actually stole this from Ed because it's such a great little thing. This is Ed's load profile, Ed Naggs' load profile at HES there from he went and did it for his house. So he's consuming about 15.7 kilowatts per day. I mean, we've got some other 2 kilowatt hours, for the others. The kitchen appliance, not including the refrigerator. Refrigeration is the key. If your customer has an older refrigerator, they're going to be chewing up a lot of electricity. Lighting's a big thing. So when you go through and you're sizing a system, not only do you want to size the system according to the customer's loads, but you also want to go in and size and see if you can reduce inefficiencies in the customer system by moving things over to different types of power sources, or reducing by putting in newer appliances or newer electronics to help reduce that electricity consumption. Some of the things to consider while you're doing that, while you're doing the sizing is first of all, days of autonomy. Stay away from the days of autonomy trap. Most customers will call you up and they'll say, yeah, I want to buy a solar system for backup, but I want 5, 6, 7 days of backup time. Unless they're willing to open up their checkbook and pretty much give you everything that's in it, most customers, you're looking anything over 2 days of autonomy is going to cost them way too much money versus what they could do if they were running a fossil fuel or some sort of generator to back it up. You want to watch out for deficit cycling. This is where your customer's battery bank is, believe it or not, oversized. And deficit cycling, basically what happens is the customer, hopefully the installer is installed and he's ensured the batteries are 100% charged, he drives away. The customer starts using their system, but then what they do is they take it down to 50%. They go to charge the battery up, and most of all the inverters, charge controllers, whatever nowadays, have this funny little green light on it that says battery full. Unfortunately, the green light's working just based off voltage in most all devices that I'm aware of. The XW, the Outbacks, the Magnums, even the Sunny Islands. Some of those voltage counts, some of those calculations are done based upon voltage. And so what will happen is that your customer, even though they're supposed to run their generator for 6 or 7 or 4 or 5 hours to get that battery to 100% state, the battery doesn't really get to 100% state because they go and they shut the generator off because the inverter says my battery's full, or the charge controller says my battery's full. So what ends up happening is day 2, the customers use it down to 60% depth of discharge, it gets up to 70, and then it starts just sitting there between, and then the batteries sit there between 80 and 60% or 80 and 40% state of charge, and the batteries sulfate. And then what we see on this particular case is the customer gives us specific gravity readings in the 1200s and wonders why the batteries are starting to fail, or you're starting to have problems with capacity issues. So believe it or not, what I'm trying to tell you here is when you live by the go big or go home mentality on size of battery banks, typically you end up getting yourself or your customers into trouble, because that too large of a battery bank compared to the charging source will cause you troubles in the back end for making sure the batteries don't sulfate. Depth of discharge. Most batteries, all battery manufacturers publish depth of discharge cycling charts. These are the published charts for our Series 4000s and Series 5000 series batteries. You know that the Series 4000 batteries, if you're going to do 20% depth of discharge cycling, you're going to see roughly 2,000 cycles out of your battery. Most installers will base their customers' depth of discharge cycling on the 50% depth of discharge, because that's the most economical between the cost of the batteries, cost of the panels, cost of running diesel. Typically is about 50% is about the most economical. And then the last thing to look at is another thing to look at is nominal battery voltage. 20 years ago in this business, most systems were 12 volt and 24 volt systems. One of the biggest drawbacks of having a 12 volt system is the size of your cabling. As we all know, both lead and copper have gotten more and more expensive over the last decade. You want to try to limit the amount of copper that you have in your system. You want to try to limit the amount of lead you have in your system, because it's not cheap any longer. If you have for example, if you have a 2800 watt 12 volt inverter, you've got to have 4 watt battery cable throughout your system. That same wattage at 48 volts, you could get away with 1 watt battery cable, you know, between your inverters. So it's very important to make sure you follow the manufacturer's instructions for the inverters of what battery cabling there is. There's a reason why most battery manufacturers or most inverter manufacturers oversize their cabling, is because most of the inverters nowadays can surge 2 to 3 times the power. That means, just to give an example, on a Radian 60 or 6048, you're running 18 kilowatt surge for 2 or 3 minutes. That's 300-400 amps of current, easy. So a 2 watt cable for a couple minutes, 300-400 amps is okay, but if you're doing it continuous, you may have to upsize the cabling. The last thing to understand is discharge rates. We all size our battery banks at a C20 rate, because there's 24 hours in a day, and you're typically doing about a 4-hour charge. So typically the C20, C24 hour rate is what we're sizing them to. This is a spec sheet for the old S530. What I've highlighted here is the discharge rates for the old S530. What you have is a 20-hour, what's going on there? You have a 20-hour discharge rate at 1280 specific gravity. That battery is rated at a 400 amp hour capacity battery. Okay. If I place 20 amps of current on that battery, it's going to last 20 hours before my voltage per cell drops below 1.75 volts per cell, or an 1175 specific gravity. Okay. Which means that battery is 100% discharged. If I take that same exact battery and I put 65 amps of current on that battery, then that battery is now only rated at 260 amp hours, and it's only rated at a 4-hour discharge rate. So what to keep in mind here is, if you've sized the system for a certain load rating and your customer starts putting more load on those batteries, they're not going to last as long as they would when you first designed that system. Best way to explain it to your customer, I found if you've got a guy in the wheelbarrow and you push him uphill and then you drop another guy in the wheelbarrow, you're not going to go as far. Another way to explain it is you put 30 liters of gas in your tank, or petrol in your tank, you drive it at 250 kilometers an hour, you're not going to get as far as if you've driven 80 kilometers an hour, because you're going to use up a lot more fuel. Um, the other thing to look at, one of the ways to look at is if you're sizing this, say you had a set of 400 string of 6-volt 400 amp hour cells in a 48 volt system. You're going to want to charge those batteries at the 4, 5, or 6 hour rate, which means you're going to want to have a charge rate of 40 to 65 amps of current. Actually, it's actually 50 to 65 amps of current, and the reason for that is if I have a 40 amp charger going into this 400 amp hour battery bank, my total charge time is going to be about 6.5 to 7 hours. Based on a 40 amp charger. If I have a 65 amp charger, my charge time is going to be about an hour and a half shorter, just because of the initial bulk stage. You can really go up to about 20% of the C20 rate, so you could really put 80 amps of current charge into these before you start causing heat problems. Once you get above that 20%, you can have heat issues, especially in hotter environments. If you get the Southwest United States or a hotter environment, I'm not sure exactly who's listening, but I don't think up in Canada you're going to have too many problems with heat issues. But I would try to stay within that 15 to 20 or 10 to 20% rate, 10 to 20% of the C20 rate. So you're looking at 40 to 80 amps of a max charge for that specific battery. As for the all battery manufacturers, like for example the S550 that we manufacture today is a 550 amp hour battery rated at a C100 discharge rate. That 550 amp hour, that C100 discharge rate means that if I placed X amount of load across the battery, it would last 100 hours. All battery manufacturers do this. The 1725s, the 1660s, the model number is all based on that C100 rate. If you're using a sunny island, you need to enter in the C10 discharge rates into the battery settings. Otherwise, you're going to have issues because the sunny islands are based on the C10 rate. If you enter the C20 rate that you designed it for, then what will happen is your charge curves, your charge information will come off, will be off. So, sizing of a battery bank, this is typically what I'll do. Again, there's I probably didn't say this before, but there's more than one way to skin a cat. This is the way I skin the cat when it's coming up to me, is I'll take that 15.750 kilowatt hours divided by 48 volts for my nominal battery bank voltage. That'll give me a 328 amp hour battery. Assume 50% depth of discharge, multiply that 328 by 2, that means I need a 656 amp hour battery for every day of autonomy. But then I add 15% to that number for losses. Depending on where you're at, you're going to add 10, 20% for losses in North America. If this is an installation in Kenya or South America, I might add 25, 30% for losses based upon how I know they're going to install the system. So for this particular battery, you'd need 754 amp hour capacity batteries. So the battery I would probably be looking at here would be a couple strings of S550s or a string of 6CS 25s would probably be the optimum. So there's always more than one way to skin a cat. The Series 5000 are going to last longer, less parallel strings. The Series 4000s, they're going to be the most economical feature, but you're going to have parallel strings that you may have to do a little bit extra maintenance. Talking about maintenance, this is an actual email that I got from a customer about a year and a half ago. If you guys want to go through and read through it while I'm talking, one of the biggest issues that you need to make sure when your customers or that you are doing maintenance on a battery bank is you have got to isolate the battery bank from both the charging sources and the load sources while you're doing maintenance. I've been guilty of doing maintenance to batteries while they're running. If you're cleaning off a connection or you're cleaning off corrosion off of a terminal and you're scrubbing it and the batteries are charging, you have to remember what's coming out of that battery: hydrogen gas and oxygen. And if you get hydrogen gas coming out of that battery and you expose a spark, there's a good chance that you're going to get an explosion. Sometimes batteries blow up nicely and they blow the top off. Sometimes they blow up ugly and the entire battery fails. It's not a good thing when it fails the second way. So be very careful when you're doing any kind of maintenance, and it's very important to make sure you have someone with you while you're doing it. So some of the things you should have, some of your tools you should have while you're doing maintenance is, of course, the coworker. You got to have a coworker. You got to have a decent pair of gloves. If I'm going to be playing with a lot of, if I'm filling up a dry battery and I'm dealing with a lot of acid, I'm going to wear gloves that are all the way up to my elbows. Depending on the amount of acid or depending on what I'm doing, is I'm going to have safety glasses or a full face mask. When I do battery autopsies, I'll wear a full face mask. A good hydrometer or refractometer, not to hit on Canadian Tire, but the Canadian Tire hydrometers, they little cheap E7 $10 ones tend to measure a little high or a little low depending on a lot of different factors, but the shake factor from the customer or whatever's going on. I tend to recommend there's a refractometer called the X-Tech RF40 or RF41. I'm pretty sure that HES probably sells a hydrometer or decent hydrometers or refractometers. Would not believe how many customers I ask what's the specific gravity measurement, and they said they don't have a hydrometer to measure it. Distilled water, deionized water, or reverse osmosis water can be used to top off the batteries. Don't let them use tap water. Don't let them use rainwater. Don't let them use water that's been collected off an air conditioner coil. All that stuff has contaminants in it, and all that stuff will eventually contaminate the inside of the battery, which will cause premature failure on the battery. Having some sort of post cleaner, wire brush, sandpaper, that way you can clean the posts or clean corrosion off terminals. Having some sort of baking soda or soda ash. Basically, what you do is I'll take about 2 cups of warm water, mix it with a cup of baking soda, and then use a towel, dip the towel into the solution when it's still dissolved, and wipe down the battery tops, wipe down the batteries in general, with the tops on. Typically, pouring the solution onto the battery is not a good idea, because if it sprays into the battery, then you start neutralizing. If it gets into the battery, it neutralizes the acid and causes problems. Putting some sort of dielectric grease on the terminals is a good idea. Petroleum jelly works. It's okay, but it also has a lower melting point, so it'll cook off. Eye wash kit's a must, and then of course removing your jewelry, no open flames. Polyester clothing is best. Well, polyester clothing works. It doesn't react to the acid as much as cotton would. Cotton tends to. We all have a pair of Holy jeans. I like to wear my Holy jeans to trainings nowadays, because people get to see that what happens to your jeans when you're wearing and working on batteries. You can even get rubberized aprons that you can wear. Again, all this stuff. If you guys, I can send HES the information of where to get this stuff. So. Here's some pictures: rubber gloves, refractometer, hydrometer, electronic hydrometers, goggles, something to wear. So most common cause of failures of batteries, probably the number 1, number 2 causes is either overcharging or undercharging. I'd say 95% of all the warranty claims that we see, customer settings are too low. They're not charging them high enough, or they're over equalizing. They're kicking them every month with an equalization charge when they don't need to, when they should just be upping their charging voltages. Watering issues. When you overwater a battery, when you overfill the battery, what ends up happening is as the battery is charging, the water expands out of the terminal, or out of the fill tube, and ends up on the top of the battery. That's just normal expansion. Underwatering, of course, is a problem. We all know what causes that. Improper watering, not using distilled water or deionized water, or even RO, reverse osmosis water, it'll actually induce hard metal or metals into the battery, which will cause problems. The last problem is, of course, loose or dirty, high resistive connections. Terminals melt off, loose connections, over torque terminal connections. There is such a thing as over tightening a battery, where it'll actually concave the battery post and the battery post will melt. I've got some pictures in this presentation to show you. Corrosion, once there's corrosion, that means there's either a loose connection or the batteries are being overwatered. frayed or damaged cables. A lot of folks like to use the very flexible welding cable. If that cable's a little too small, then what can happen is it can actually develop it can actually damage over its lifetime and cause problems with loose or dirty high resistive connections. So on a brand new battery bank, you should monthly be looking at the specific gravity readings, loaded and rested voltage readings. You should be checking your water, checking out, making sure your ambient temperature battery isn't getting too hot, inspecting the cells to make sure there's no corrosions or leaking or anything going on with the battery bank, and then topping off with distilled water as necessary. Now I say this to do it monthly on a new battery bank, because every battery bank is different and every customer is different and every system's different. So you can have 10 customers and you can have a customer who looks at his batteries every 3 months and is just fine, while you have the next customer down the street who uses batteries more and has to look at them every 15 to 30 days. So it's very important for your customer to develop that relationship, or you to develop that relationship with that customer or battery bank, to determine what the maintenance schedule should be. But as a base on a monthly basis, initially for the first 6 to 9 months, you should be looking at it monthly. On a quarterly basis, you should always, especially a flooded battery bank, you should test and make sure the ventilation works properly. A lot of times we'll get calls where batteries have exploded and ventilation didn't work or something happened. You should check for the high resistive connections. Do not do the tug test. What I mean by tug test is grabbing a hold of the battery and tugging on it, or the battery cable and tugging on it. The tug test tells you that the connection may be tight, but it doesn't tell you if the connection is welded. If you've already developed a loose connection and it's welded, it's just going to continue to heat up and eventually cause a failure. You want to put a wrench on it, back it off a turn or two, and then retighten it. Another great tool for looking at these is looking at the battery while it's charging with an infrared temperature sensor. You can get them at most hardware stores for 15, 20, 30 bucks. You can do cheap ones pretty easily. That'll easily. I was just at a bank in the beginning of the summer. Customer had 2 strings of banks, 2 strings of 2-volt cells. One string was doing fine, the other string was not doing very well. Turned out he had a loose connection on one of his series connections, and it was causing problems with that entire string. So you want to verify your charge output, make sure your bulk or absorption settings are proper. Again, settings are not set it and forget it. Most customers are going to have to adjust their charge parameters regardless of who makes the battery once, twice a year, depending on summertime, wintertime, depending on how big their PV array is, depending on how much load they're placing on the battery bank. You need to verify that those settings are proper based upon what your specific gravities are telling you. A little higher specific gravity might require a little lower voltages. A little lower specific gravity is going to require a higher voltage. Of course, check the cells for cracks, leakage of evidence of leakage, stuff like that. And of course, making sure your battery bank is properly grounded is also important. A little bit about battery charging, Surrettes in general, and there's a lot of reading here, so I apologize for that. I threw this together pretty quickly. A 12-volt battery bank has 6 cells. 24-volt battery bank has 12 cells. 48-volt battery bank has 24 cells. Each nominal cell voltage is about 2.1 volts. So a 12-volt battery, fully charged and resting, is going to measure between 12.6 to 12.7 to 12.8, depending on the chemistry. A 100% discharge battery is going to measure 10.5 volts. Okay, a 2 volt per cell or a 12-volt battery that measures 12 volts resting is at 50% depth of discharge. Okay, those are some things to keep in mind. On the 10.5 volt settings, most of your inverter manufacturers set their low battery cutoff setting at that 10.5 volts, which means you've already 100% depth discharged the battery by the time you shut that inverter off. So that might be a setting you might want to look at to adjust up and down. Typically, I'll adjust it to I'll adjust it to about 1.85 to 1.9 volts, and go from up or down from there, depending on the annoying factor for the customer. If the customer complains about having disconnections. So if you are using 4 Rolls batteries, and this is where you want to get your pins out, 4 rolls batteries. If you're using temperature compensation on a brand new battery bank, you are going to want to start your bulk absorbed voltages about 2.45 volts per cell. That's 14.7 at 12 volts. That's 29.4 at 24 and 58.8 at 48. Okay. The reason for that is that by setting at that 2.45 volts per cell, what you're doing is you're allowing the inverter to adjust the battery charge voltage based on the temperature of the batteries. And you're setting the voltage about the midpoint, a little bit higher than the midpoint, to make sure you give the inverter room to adjust it. A lot of customers will leave it at the default settings, which is 2.4 volts, 14.4, 28.8, or 57.6 on the inverters. And what will end up happening is the batteries will sulfate over time, because the inverter is also temp comping that battery voltage up or down based on the temperature, so it's changing your absorb voltage set point. That's going to be a problem for most customers, or that is a problem for most customers. Absorb time, basically this formula works out pretty well. It's 0.42 multiplied by the C20 rate divided by nominal charge current. Okay. What that means is that if you have a 800 amp hour battery bank with an 80 amp charger, your absorb time is 4 hours and 4.2 hours, which is roughly 4 hours and 15 minutes. Okay. Float, typically 2.2 volts per cell. Equalize 2.5 to 2.58 to 2.65. I personally like to start on the low end of the EQ voltage. I'll get into the equalization. Hopefully we're not going to go too much further, but and then EQ time's about half to 2/3 of absorb time. To determine that for real, what you need to do is go and look at your specific gravity while you're EQing. Once it stops rising for 60 minutes, that's when you stop the EQ. That should be what your EQ time is. Unfortunately, size of the battery bank, size of the charger, temperature of the batteries, they all affect that. All we can do is give you a base guideline. Now for your renewable sources, what I usually suggest folks do is for the bulk and absorption on their solar or renewables, if their source has less than 10% of the C20 charge rate, I will usually use the higher voltages, the 2.46, 2.47 to 2.48 voltage. If you're above that 10%, I'll usually set it at the 2.45 volts. And the reason is that, so if you have an 800 amp hour battery bank and a 400 watt solar array at 24 volts, the 400 watt solar array is not going to do much to that 800 amp hour battery bank in a 5-6 hour Sunday. Absorb times are very different for charge controllers than they are with inverters, because usually you are below that 10% rate, and you're not going to get 4 or 5, 6, 7 hours of decent sun. So most of the time, if your solar charge controllers are going into float, that usually means that your PV array is sized too big, or it means your battery bank is too small, or it means your battery bank's sulfated. That's usually what your charge controller going to float. Now, if I have a PV array, now float voltage usually 2.2 volts per cell, but I might even set it up at 2.25 or 2.3, again, depending on the size of the array, to keep the array at a higher voltage, more power going to the batteries while you have sun to increase that overall efficiency. And of course, EQ time and EQ are about the same. So again, I'm expecting to get a bunch of questions in these charging settings. Here's some notes in the charging settings. If you notice the specific gravity falling after the first 3 to 4 months, you adjust your voltages and times up a bit. And what you want to do is you want to make small changes. Add 0.2 of a volt. Add 15 minutes to half an hour. Those type of things. Subtract 0.2 of a volt. Subtract half an hour if your specific gravities are going high. If you're not using the battery temp compensation that Outback and Xantrex and Schneider and Midnight and Morningstar and all the manufacturers sell, if you're not using the temp compensation, you need to adjust the battery charge voltage based on the temperature of the batteries and not the ambient temperature of the room that the batteries are in. So it's better to spend $20 on a temp compensator and let the controllers do it properly. For flooded batteries, it's essential that you get the batteries to a bulk absorb cycle every 3 to 4 weeks. For AGM batteries, it's essential you do it every 6 to 7 days. Be cautious of some of the current meters, as they can be confused as when the battery is full. A sulfated battery will appear fully charged to some of these meters due to the quick drop off and the quick current drop off. The current will drop below that return amp setting, which will cause it to think it's full. If anybody's seen a sulfated battery, when you put it in bulk, it'll rise through the bulk voltage. You know, instead of taking an hour and a half like it used to, it takes 20 or 30 minutes. That is the classic symptom of a sulfated battery. Here's just some absorption time calculations. You guys will have access to this. I kind of went through the formulas a couple times already. Here's the dilemma of batteries. If you use the lower charging voltages, your batteries stay cooler and you maximize the service life. The problem with it is that you have slow charge times. It's going to take more fuel, more energy to get those batteries to a full state of charge. Sulfation is going to occur, and this is going to require more frequent equalization cycles. Higher charging voltage settings, faster charge times, you get more consistent capacity readings, you have less sulfation issues. You get more gassing, more possibility of corrosion on the terminals. You're going to have to water the batteries more often, and the higher temps can cause overcharge issues or active material shedding. This is the dilemma of batteries, where you have to weigh with your individual customers what's good and what's bad and where you need to work with. So equalization. I can't tell you how many folks I get that call me up and say, yeah, I equalize my batteries every single month and I don't know where my specific gravities are doing. The batteries just don't work, and yada, yada, yada. The only time that you should be equalizing your batteries is when you see more than a 0.2020, 0.025 or 0.030 difference between the specific gravity points. Equalization is very hard on batteries. We call it equalization for a reason, because you're trying to equalize different specific gravities to a close range. You don't want to continuously equalize battery banks, because what it can is the over equalization can definitely accelerate plate shedding, and plate shedding is not a good thing. A battery bank that's being properly charged, once getting to a full state of charge once a month, being properly maintained, maybe you might have to equalize once a year at best. The customers that are hammering the living daylights out of the batteries just because they don't want to charge them or they don't want to run a generator, they're actually accelerating the failure of a flooded lead acid battery. One of the things that some of the charge controller manufacturers do is they'll have that auto equalization. Again, depending on the size of the array, if the array is large compared to the battery bank, over 10-15% charge rate, so you have an 800 amp hour battery bank and you've got 160 amp, your array is capable of doing 160 amps, you may want to back off the equalization cycles, do it once every 40 or 60 days instead of once every 30 days, or have the customer do it manually based on his specific gravity readings. So equalization is not the fix-all. So I've already kind of gone over the common reasons battery fails, so I'm going to go over some show and tell, and we'll get into some pictures. These two pictures are from a battery bank that were up in Canada, and unfortunately these batteries froze. These batteries were in an outside shed, and they were inside of a shed. It got extremely cold. The batteries were left in a state of discharge, and the water inside the batteries froze because it turned into water because they were sulfated. And this is the kind of damage that you'll see when a battery freezes. Typically the case will blow out at the sides or the front versus the top coming off. This is a system that was installed in the US. I don't know if you guys can see this main picture, but this was actually 3 parallel strings. The third string went to the distributor for testing, where we found out that the batteries were in trouble. If you look at where the temperature sensor is placed, it's placed in the top of the batteries, and there's absolutely no spacing between the batteries. The other issue is these batteries are mounted outside. I don't know if you can see it, but this right here, that's the top cover. It's just a piece of plywood that goes over the top of the batteries. Not a good thing. Here's the placement of the temp sensor. The temp sensor is on the top of the batteries. The batteries should have, in the summertime, about 1 to 3 inches of space between them. In the wintertime, they should have either insulation or they should be moved closer together, especially if you're in a cold environment. If you look at the plate, we actually did an autopsy on some of these batteries, and if you look at this plate, the plate's gooey, which means the specific gravity was way high. And then the other issue is that the active material shedding off the plate is a bad thing. That decreases your capacity of the batteries, which will eventually cause failure. What's going on here? There we go. There's the next one. And these are typical loose connections. The first loose connection, and my drawings just didn't disappear, so this is going to get a little messy. There we go. So if we go back to this one, if you look at this connection here, you can actually see where the washer bit in to the terminal. This one, the terminal just completely melted off. These are loose and or over tightened connection. When the washer bites into the terminal like that, it's actually concaving the terminal, and you're losing surface area in the terminal. So it's just like Goldilocks and the Three Bears. There's too hot, too cold, and just right. This is too hot, this is too cold, and then of course a good-looking terminal is just right. Let's see here. How did I do that? I'm sorry, guys. I'm having technical difficulties here. Oh, here we go. Maybe that'll work. All right. There we go. Here's the next one. Again, a couple more loose terminals. You see how they've melted around the bus bars. So again, these are loose terminals. This is exactly what it looks like when you have a loose connection. We get lots of folks that call us up wanting to cover these under warranty just because they think that this is a manufacturing issue. The next issue, this is a perfect example of a hydrogen ignition or the top being blown off. If you notice that the top cover has failed, we've got the crack in the top cover. This is actually one of the new S550s, and this was actually in Jamaica, and it was installed in a box without ventilation. And when they had a loose connection on the terminal, and you can even see it. Actually, it wasn't loose, but it was over tightened, and it started to arc. You can actually see it right there where the terminal was actually over tightened. You can see the lip of the washer. So this was a hydrogen ignition which caused the top to blow off. Not a good thing. This next one is to dispel a couple of wives' tales about batteries. A lot of folks think when your batteries start to decrease in capacity, they'll just dump out the acid and add new electrolyte. Not so. All you're doing is increasing the electrolyte content in the battery, and that higher electrolyte content will cause a problem with eventually causing problems with the plates. The other wives' tale is putting batteries on concrete. You don't have to worry about that with Rolls batteries. We use a polymer chassis that does not conduct heat or cold into the battery, so that it's not going to cause problems and draw down your battery capacity. Let's see here, and I think here's some AGM batteries. These batteries were susceptible to over 125 degrees Fahrenheit of heat. That's what caused the cases to blow out, to balloon up. Basically, what's happening is the case itself gets hot, and the air expands the case. The hot air expands the case, and it pushes it out. There's no plates or anything expansion in here. It's just being pushed out. It's ballooning out. This battery bank is probably within a couple of weeks of actually exploding. At this point in time, it didn't explode. We were able to make sure the customer didn't cause more problems. But this is overheat, over temperature issues. You want to make sure you install your battery bank in a cool, dry environment. Otherwise, you can run into problems like this. Here's another battery bank that's on its way to doing something like that. Thank God it's not Rolls batteries. But the biggest issue here is the batteries are stacked onto each other. You have absolutely no airflow between the batteries. Not to mention you have the large distiller that's sitting next to the batteries that's on wheels that can easily be pushed into the live battery connections. Not the greatest installation. And last but not least is my favorite in the world, is mixing cells. This customer has mixed a C&D forklift battery with traditional Group 27 batteries from what it looks like, all for one system. Not something you want to do. One of the problems with mixing cells is you have different capacities. If you have a high capacity with a low capacity cell, the high capacity battery is going to degrade to the point of the low capacity battery. The other thing is, you know, old and new batteries. When you have a battery, say you have a customer who buys a battery bank today and he wants to add a battery bank a year later, that new battery bank will degrade in capacity to the old batteries, and there's absolutely nothing you can do about it. AB switches, specified charging, it's going to degrade regardless of what you do. So it's important to make sure the customers understand that, know that when they make the initial purchase, that they buy the battery bank size, or they're going to have to deal with the mixing of the batteries later on. It's not something I would suggest you do. At this point, that went exactly an hour. I wanted to go about 15 minutes shorter, so at this point I want to open it up for any questions we got. I appreciate everybody for coming and listening to me.
Thanks, Steve. Really appreciate that. It went over really well. And thanks everybody for attending today. If you do have questions, just type them in and I can post them on your behalf, and Steve will be able to answer them, I'm sure. We do have one question here so far, Steve. That would be, what happens in the battery when you overcharge it?
When you're overcharging a battery, what usually ends up happening is it raises the heat, the temperature inside the battery, and it'll cause the active material to flake off. If I go back, I'll go back to the presentation. Hopefully the gentleman's still on. This battery was mounted outside on the western side of the house, and it caused the heat. Overcharged batteries look much like this also. Let me highlight it. Overcharged batteries, when you autopsy them, you see a lot of active material loss in the battery, such as what I've just circled. Can everybody see that circle? So overcharged batteries see this. So what ends up happening is the heat rises, that active material falls off, and then you lose capacity.
Okay. Next question is actually a general question, and that is that we are going to be hosting or posting this on our YouTube channel. You can get to our YouTube channel on any page of our website. In the footer, you'll just see the Twitter, the Facebook, and the YouTube logos on the bottom left. And if you click on the YouTube, it will take you to our channel where you can, of course, watch this and many other webinars that we posted. Sorry about that. We're back. What was the cold temperature you mentioned the battery will freeze at, even if fully charged, and when at 50% charged?
At 100% stated charge, 1265 to 1280 specific gravity, a flooded battery will not freeze until negative 94 degrees Fahrenheit. A battery that's at 50% state, which is 1200 to 1220 specific gravity, will freeze at 20 degrees Fahrenheit.
Okay. Our next question is, can I oversize the solar array, say a 500 amp hour battery with too much solar, assuming charge controllers are being used?
Yeah, if you put in the great thing about the solar charge controller is it's going to regulate based on the voltage. So if you have an excessively large PV array, and you're using temperature compensation, you can go as high as the 30%. You can put in say it's 1,000 amp hour battery, you can put 300 amps of current into that battery. If you're properly using the temp compensation probes, you're going to keep the battery from overheating, and it's going to keep your batteries charged longer. The sweet spot is still that 15 to 20% for most people. When you get up in the northern areas, it's amazing that I was up in Alaska a couple of years ago, and it was a little 1500 watt array on a 1000 amp hour battery. It was amazing how much PV was coming through in the middle of winter. So, so you definitely want to keep that in mind.
Okay. And this actually goes on to what you just said a second ago. Should you limit the temp comp voltages on the charge controllers?
Up north, no, I wouldn't, because you've got such a wide range of temperatures. In the summer, it gets pretty warm. In the winter, it gets pretty darn cold. So I would leave your temp comp limits wide. I think Outback does that on maybe midnight still. I'm not sure about I'm not as 100% familiar with the Schneider and the other the Morningstar controllers, but the temperature compensation is 5 millivolts per degree C per cell. So if you have a 48 volt battery bank, it's going to be like 192 millivolts per degree C. So for the entire battery bank.
Okay. Sorry, go on.
Oh, I was just making sure. Did that answer the question?
I will check with. We may follow up with that.
Okay.
There's a really technical question that we might get you to ask offline, Steve. But there's an easier question. Is a client's asking the viability of using one of those pulse type battery desulfators?
We've done some testing on them, and I've done some testing of my own on them. For these larger capacity batteries, they tend to not work very well, because what they're doing is they're just putting a high frequency, high voltage pulse into the batteries, and these larger capacity batteries basically absorb that without even seeing it. Those pulse type chargers, they're pushed quite a bit in the market, but they don't do a whole lot. On the smaller cell batteries, the Group 24s, the 105s, those smaller cell batteries, they tend to help as long as they're with the installation from day one. But if you put them in to fix a problem, they're just a Band-Aid 99% of the time, at least from what I've seen. So we don't normally suggest the pulse chargers.
Okay. Okay. Well, if there's a few other questions here which we'll answer on through email. If anybody else has any other questions, please do send us an email to ourselves or to Steve, and we'll be more than happy to help you with your solutions, with solutions to your questions and problems. At this time, I'd also like to just mention we're doing a Solar 101 training in September, right at the end of the month, September 30th, and this is in Calgary for it's a half-day training, and it's preceding the Can't COS conference. For anybody that's interested, this is a good way of getting into the solar and figuring out a whole ton of stuff. Topics that are going to be covered are grid-connected systems, the Western Canadian solar market, how panels work and are made, what's in it for end users, customers, and working with local utilities. So thank you everybody for coming today. We really appreciate it, and thank you very much, Steve. Another excellent presentation.
No problem, man. Well, hopefully I got everybody's questions answered.
Okay, everybody have a good day, and like I said, we'll contact everybody through email with the remaining questions.
Okay.
Take care. Cheers.